So now let's go ahead and apply the Rice expression to do some of these problems to see that actually it's kind of neat, kind of simple to see how the math works. Let's take the easiest case, the case of AB. This is going to be a case that's going to look an awful lot like when we were looking at water before, making protons and hydroxides. AB goes to make A plus and B minus. I set up a Rice expression for it. And watch the first part of all solubility product problems. This part doesn't matter. Why? It's a solid. It's a solid throughout. I ignore it because it has an activity of 0. How much A plus and a B minus do I have to start? I start with none. And now it starts to dissociate. As it dissociates, the reaction is shifting to the right. I'm making X. And because stoichiometrically I make the same amount of A and B because it's 1 to 1, at equilibrium, I have X of each. So KSP is equal to A plus times B minus is equal to X times X is equal to X squared. And therefore, the KSP is equal to X squared. And therefore, X, which is equal to the concentration of the A, which is equal to the concentration of the B minus, is equal to the square root of the KSP. Wow, that is a great result. This means that when I look at salts that are of the form AB, this can be sodium chloride, NaCl. This can be CaO, calcium oxide, one of each. This can be anything that's 1 to 1. So as long as the charge of the cation and the anion are equal. What is the KSP? Rule of thumb, square root. So KSP is 10 to the minus 5. What is the molar solubility? The square root of 10 to the minus 5, 10 to the minus 2.5. KSP is 10 to the minus 40. What is the molar solubility? Square root, 10 to the minus 20. That's why when we were looking at those problems just a second ago, and I showed you values for the KSP, and I wanted to talk about the concentrations of these sparingly soluble salts for the cases where I had a 1 to 1 ratio of the cation to the anion, rule of thumb, form AB, square root of the KSP. This became 10 to the minus 14. This one becomes 10 to the minus 5 molar. Very nice. This is the kind of problem you hope to see on tests, because then you just take a square root. Notice the similarity to when you're doing acid-base problems where you have H plus and OH minus. And so it's just the square root of the Kw. That's how we got the value of 10 to the minus 7. That's how we got a pH of 7. Now, unlike acids and bases, where I make a single H plus, OH minus, where there's typically one proton that comes off in most of our initial problems, instead of that, when you're dealing with salts, you have a dissociation where it's possible that you have multiple species going into solution based on the stoichiometry. Let's consider this case right here, in which we have an A double plus and a B minus that comes from something of the form AB2. Now that I've got 2 of these for every one of these, when I set up the KSP, on a certain level that seems okay mathematically. All I have to do is put a square term up here. But let's look what happens in the Rice expression to see how I've approximately complicated stuff. Of course, I can ignore this. That's a positive. Now I'm going to start with none of each, because in these particular simple problems here, it's a pure water solution until I dump everything in. I'm going to be making X of the A double plus. Guess what? I have to make twice as much of the B, because for every one of the A's, 2 of the B's form. So now you see that the math is not simply a squaring sort of thing going on. At equilibrium, I've got X of the one, 2X of the other. I've got to stick these into this expression here. This becomes X. This becomes 2X squared. The result is 4X cubed. When I have compounds of the form AB2 or A2B, this is the expression that allows me to figure out the molar solubility. The molar solubility found this way. I bring the 4 over underneath the KSP, and I take the cubed root to solve for x. So if I've got a compound of this form here, I've got to take the KSP, I've got to divide it by 4, and I've got to take the cubed root. So I take a look back at an example like that. Here's one. Here's an example like this. CaF2 goes to make calcium and 2 fluorides. I need to divide this number by 4 and take its cubed root. At this point, you remember you're in Laude's class. You remember that he doesn't let you use calculators. And so you're expecting some help here in problem solving. And here's a problem solving tip. Do you really think that dividing by 4 is as important as taking a cubed root of a large negative exponent like this? No, it's negligible. So I'm going to simply say that that divide by 4 isn't all that important here. If I have my calculator, great. I'll go ahead and divide by 4 and take the cubed root. But exponent math allows me to take this value right here and simply divide by 3 in the exponent. I've ignored the divide by 4 of the overall number. So the answer here is the molar solubility is about 10 to the minus 4. It's not exact, because I haven't taken into account that factor of 4 that I didn't divide by, but it's close enough. Well, you're starting to see that as I work these problems, there are some patterns that are going to develop. If I show you a compound of the form A3B going to dissociate to make 3 A pluses and a B minus 3, and you set it up, you know what's coming. You can ignore this right here, none of this to start. I'm going to make x of this, I'm going to make 3x of that, which means that my KSP, isn't it great how Rice expressions work? Everything's always the same way, is going to be a value of 3x cubed times x, and therefore KSP is going to be equal to, oh, look at this math I have to do, that's 3 cubed, that's 27x to the 4th. In other words, my x value for my b, in this case here, is going to be equal to KSP divided by 27 4th root. Hey, what do you know? Here's an example like that. Here's an example right here. Iron hydroxide making iron and 3 hydroxides. Hey, that's of the form A3B or AB3. So I'm going to take this number right here. I'm going to divide it by 27. I'm going to take its 4th root. But wait, it's Laude's class. He's probably going to tell me the 27 doesn't matter. And sort of it doesn't. It's an order of magnitude. But not compared to 10 to the minus 40. Relative to that, not so important. And then I'm going to take the 4th root of this. 10 to the minus 40 divided by 4. The molar solubility is 10 to the minus 10.